Welcome to the Fuel Pulse Show podcast. I am your host, Eric Bjornstad, and I am your guide through the ever-changing world of fuel. The Fuel Pulse Show podcast is for anyone who uses fuel or who has things that use fuel, and that means whether at work or at home. And it's especially for people who work in positions where they may have to manage some supply of fuel so that it can be used in some capacity to get the job done. Whatever that job may happen to be, which means the Fuel Pulse Show podcast is for all of us. It's for all of you out there. So, what are we going to talk about on today's episode? Well, we have talked before about the fact that today's fuels are not the same as they used to be back in the day. The fuel, the gasoline that you buy today at your local gas station is markedly different than the fuel that Ron Howard was putting in his hot rod in American Graffiti. And a big example of what this difference is the fact that today's gasolines have these things called oxygenates in them. And when we say oxygenates, we usually mean one of two things, either ethanol or some compound that they call MTBE. Now, looking at history, anytime you want to look at how things are in the present, where you are in the present time, there is always an interesting story about how you got to the present time. And so it is with this thing, MTBE. It's a story of problems being recognized, important problems, serious problems, problems needing solutions. And then it's a story of people getting together to say something needs to change and then making those changes. And so we want to understand that story. On today's podcast episode, we are going to talk about what these things in our fuel called oxygenates are and why they matter. We're going to talk about the reasons we started using oxygenates and the problems that we had here in this country that really forced that issue. And then, as we do that, what we will find is that what we thought was the ideal solution turned out to bring some unintended consequences of their own along with it. And that required us to move in another markedly different direction. But it's not all bad, because the more that we look at our recent history, the easier it is to see that we have come a really long way towards making things better. And so that's right, not everything is doom and gloom. Sure, there are always things to improve on, but if you don't know the full story of history, if you don't know how things used to be, it can be easy to miss the fact that some really big, positive, substantial changes have come along. And those changes, they're things that we are so used to now, so used to having around now. We don't think anything of them today. But those things, they've made life better. They've made the world better. And maybe that should give us some hope for the future in some other areas. So let's get started with this discussion. So first question, oxygenates, that term that I was using, what the heck are they? What is an oxygenate? And what are these things called ethanol and MTBE? Well, ethanol and MTBE are both examples of members of classes of molecules in chemistry called alcohols and ethers. And there are thousands of examples of each kind of thing. There are thousands of alcohols from a chemistry standpoint. There's thousands of ethers from a chemistry standpoint. But the commonality with all of them is that they all contain molecular oxygen. So if you were to mix some of those into, let's say, gasoline, they would all raise or increase the oxygen content of the gasoline that they were being put into. So that is the baseline answer there as to what they are. But you might raise your hand and say, well, who cares? So what? Well, or you might ask a follow-up question. You said putting them into fuel. Why is this something that somebody would want to do? Well, simply put, or the simple answer is adding more oxygen when you're talking about fuel, right? Burning fuel inside of a car engine. When you're talking about adding more oxygen to the combustion process, that kind of combustion process, any kind of combustion process, the more oxygen you have, the better, more complete combustion you end up having. Now, if you remember from way back in the day in your high school chemistry, and you talk about combustion of hydrocarbons, um, you say complete combustion of hydrocarbons results in two combustion products. If you have perfect combustion, you get carbon dioxide, a certain amount of that, and you get a certain number of water molecules. CO2 and water are what you get if you have perfect and full combustion. So let's say that you have a five carbon hydrocarbon like pentane. If you were to burn it completely, then you would get a certain number of water molecules, H2O, and you would have five molecules of carbon dioxide, CO2. And that means stoichiometrically that you need, in order to have perfect or complete combustion, you need to supply enough atoms of oxygen into that process so that you can make five molecules of carbon dioxide, which is 10 oxygens, and then however many water molecules are going to go with that. And that's a certain number of oxygen molecules above that. But let's say that you're in a combustion situation where you don't have the ability to supply enough oxygen to make that happen. So if you're in that kind of incomplete combustion scenario, what will you get if you don't get H2O plus CO2? Well, low oxygen influences, first of all, the formation of carbon monoxide. So when you don't have enough oxygen, you're not going to get CO2 formed, you're going to get CO formed. And that is bad for air quality. Carbon monoxide, as we will find out later, is bad for air quality. Also, if you don't have enough oxygen for complete combustion, then you're going to get increased levels of what they call PM emissions. PM is an acronym, stands for particulate matter. Basically means you're going to get a bunch of partially burned, smaller hydrocarbon molecules, as opposed to having it burned completely and all forming carbon dioxide. So, making sure that you have enough oxygen available to do ideal, complete combustion of gasoline is pretty essential. But if you don't have enough oxygen, where can you get it from? How can you remedy that? Where can you supply more oxygen from? Well, in any combustion scenario, the primary place that oxygen is supplied is through the air. So you would say, well, I'll just add more air. But you can't really do that in an automobile engine. They're not really engineered to allow you to do that. So that's not really an oxygen when you're talking an option when you're talking about burning gasoline. But you can supply more oxygen elementally by supplying it through the fuel's composition. And that is what mixing an oxygenate into your gasoline, that is what that is supposed to do. And so that is the basic reason why they're mixing in things like ethanol or MTBE into gasoline, because supplying more oxygen makes better emissions and better combustion. So even though you might not have heard about oxygenates like ethanol or MTBE until, the past 10 years or until recently, they actually have been around a lot longer than that. Over the past 3 or 4 decades, oxygenates have been used in fuel, but not necessarily to help with air quality, but rather to increase the octane value of that gasoline. So let's go back in history and let's go back to the early 70s when they had the movement. They recognized that having lead, or what they call tetraethyl lead, having that in gasoline was causing some real problems for human health and it was causing problems for the environment. And so they were going to take that out of the gasoline. So that's a good thing for health and the environment, but it's creating a problem. It's creating a need because one of the things that lead did in gasoline is it bumped up the octane rating. And now you're going to take that out. So if you're going to take that out, you need to replace it with something that will put that octane value back into the gasoline, or else you're going to have problems. And that is what gasoline refiners started using oxygenates for in the United States. It was primarily as octane boosters. So the lead phase out begins around 1973. Refiners realize they have to replace this octane loss in gasoline. And so oxygenates, these oxygenate compounds, were a natural choice to replace this octane loss because all of these oxygenates, they all have relatively high octane ratings. So if you take a relatively small volume of oxygenate, you mix it into the gasoline, and you can get a fairly significant gain in the octane value of that gasoline blend. Additionally, um, during the energy crisis, 1974, 1975, one thing they also found was they could use oxygenates if they put, let's say, 10% ethanol into gasoline. They called it gasohol, if you remember. Basically, they're able to stretch the volume of that gasoline so it helps their economics. And so in the 70s, they would use oxygenates both as an octane booster and also to stretch out or space out their gasoline supplies. So in those two uses, at least, the idea of putting oxygenates in gasoline has been around for a fairly long time. So we know that they use oxygenates to boost octane, but today that's not the only thing that they are used for, and you probably guessed that that was the case. More recently, let's say in the past 30 years, oxygenates have been used as something to help them control or improve emissions. You might say they've been used as an emissions control strategy, if you will, in an effort to reduce harmful emissions like carbon monoxide, particulate matter, also ground level ozone. So let's talk about that a little more because the whole emissions thing was really the primary driver for creating the situation that we have today. So let's go back. Let's go back and talk about the situation in the past in a little more detail so that we can get a better understanding of why they chose to do this, why they're choosing to do this now. Because in order to get that understanding, it's good to know more about what things were like back when they started thinking about this. So, go back to World War II. In World War II, I think we wrote a blog recently talking about the development of the automobile industry. And you see that in World War II, they essentially stopped making cars for like a 3-year period because they were making other things, right? Trying to defeat the Germans, trying to defeat Japanese. So after World War II, they got things cracking back up, and we saw up to that point the greatest period of economic growth that our country had ever seen. So we had this economic growth, we had rapid population growth, we had demographic trends of like suburbanization where people were moving closer to the cities. So all of those things together, they all came together to create a situation where personal transportation in the United States, lots more people, lots more families owning cars, and that means lots more cars on the road. You also had an explosion in paved roads as well, because there were a lot of roads up to that point that were not paved. So they started paving all the roads, increasing the number of highways, and so you get this just explosion of cars and trucks, this explosion of traffic, especially concentrated in the cities. And so one result of that rapid increase in the number of motor vehicles on the road was air pollution, especially in the cities. And that air pollution was having serious impacts on the public health and having serious impacts on the environment. Now, for most of us today who've grown up, I'm a child of the 80s, essentially. I was born in 1974. I came of age in the 1980s, went to college in the early 90s. That is my reality. The reality for most of us is that we've grown up in a time where we didn't really have to think that much about air quality. We just took it for granted. So when we hear about a supposed time, in the past when air quality was really bad, we find it a little hard to fully believe. It's hard for us in the 21st century to conceptualize the kind of air pollution that urban city dwellers dealt with way back in the day. Way back in the day, almost every single area in the country or every single city in the country failed air quality standards because they had all this air pollution coming not just from cars, but also from things like garbage incinerators and all of those coal-fired power plants and oil-fired power plants that did not have the emission scrubbing technologies that they have today. And so what was happening was people living in urban areas, New York, LA, Chicago, virtually any sizable urban area that you want to name, they were very concerned about the air quality, not just because of the effect that it was having on them, but definitely because of the effect that it was having on their children. So if we look at a few examples to get some perspective of this, do we just pick a place like, let's say, Donora, Pennsylvania in the 1940s. Now, Donora, PA is about 30 miles south of Pittsburgh. So it is smack dab in the Rust Belt. Lots of coal-fired power plants, lots of steel, of course, being Pittsburgh. And so there's a case in 1948 when this weather pattern developed over Donora, PA. And for those of you who are sports fans, Donora, PA is primarily famous for the fact that on the exact same day, November 21st, two of the greatest players in baseball history were both born, Stan Musial and Ken Griffey Jr., both born on November 21st in Donora, PA. That's your sports fact for the day. So 1948, you get this situation where you get this pocket of warm air that settled over the city. And what it did was it trapped the cold air beneath it. And the cold air was basically this big blanket of smog. And so for 5 days, the entire city was just blanketed in this thick cloud of smog. And for 5 days, about half of the town's 14,000 residents at the time developed severe respiratory problems or severe cardiac problems because it was so difficult to breathe. And 40 people actually ended up dying over 5 days because of the air quality out there. I mean, that's pretty bad. Let's go to the other side of the country. Go to Los Angeles. Los Angeles became famous for its air pollution problems. So in the mid-1950s, if you were to measure ozone levels in Los Angeles, ozone levels measured out at about 650 what they call ppb, that's parts per billion. Now, that doesn't mean anything to us. It's just a number. But if you consider that today, the EPA considers that the upper threshold for the amount of ozone that's needed before, let's say, children start experiencing measurable health problems is 70. And yet, back in Los Angeles in the mid-1950s, their ozone levels were 650. So about 10 times, 9 to 10 times that amount. And interestingly, one of the things that came out of that is that car manufacturers in LA, right? They began to notice that the rubber on the cars was wearing out a lot faster in Los Angeles than in other areas of the country. And it was because of the ozone levels. And so one of the things that happened was that because of the poor air quality that was in LA, they developed actually one of the earliest simple methods for measuring ozone levels, which was you take a rubber band, you stretch it and you just put it over around the jar, you leave it, and then you see how long how long it takes for that rubber band to snap. That's how you measure the ozone levels in LA. So just about everywhere, whether you're in LA, whether in Donora, Pennsylvania, New York, Chicago, almost any urban area, unless you were a farmer and still lived on the farm, just about everywhere else had terrible air quality. But, we can say that, but we have to ask the question, how are we judging terrible air quality? What things do we look at to judge air quality? And why do we pick those things to look at? Why are they bad? Well, so let's look at some of the things that go into this concept of emissions that affect air quality, or emissions from cars that affect air quality. So we look at 4 or 5 different pollutants that are produced by automobile engines that go into or contribute to the air quality picture in a given area. So the first thing that they look at is this thing we already mentioned called PM. It's particulate matter. That's all those tiny, too small to be seen with the naked eye, particles of carbon that are really just incomplete or partially burned gasoline. So you get all these tiny little particles and they end up in the atmosphere. You get enough of them in the atmosphere that they actually make the atmosphere look hazy. And they're bad because they're small enough that they can penetrate deep into your lungs. And when they penetrate deep into your lungs, if enough of them do that over a long enough period of time, you can get lung damage. So that's bad. Particulate matter is bad. CO, carbon monoxide. Everybody knows if you're in a room and there's too much carbon monoxide, it'll kill you. Walking around LA outside isn't going to have enough carbon monoxide to kill you, but it will have levels high enough that it will affect your brain and your heart. And it will affect children more. Any of this stuff that we're talking about, when we talk about how it affects people, we say it affects adults this way. And then you factor children in where they still have, developing cardiovascular systems, their brains are still developing. You can basically amplify the effects of any of these, and that's the effect that they have on children, is proportionally greater. So particulate matter, carbon monoxide, something that they call NOx. Colloquially, it's called NOx, but it's nitrous oxides, NO2 gas, NO3 gas. NOx gases are really bad for children, really bad for the development of their respiratory systems, causes lung irritation, weakens the immune system. And then, interestingly enough, if you have high levels of nitrous oxides emissions here, and then you have unburned hydrocarbons or PM here. One interesting thing that they found is that when you have both of those together and they mix, and then you have sunlight, mixing together, lots of sunlight in, let's say, LA, there's a reaction that happens and they actually form ozone, or what they call ground level ozone. And ozone is the primary thing that causes smog. And ozone itself is kind of like NOx in that it's really bad for children's lungs and respiratory systems, contributes to a lot of asthma problems, all that kind of stuff. So, 1950s, post-World War II, the nation's growing, and the nation has really bad air quality. And the nation recognizes that something has to be done about this air quality problem. It's not something that they can keep ignoring. So in the 1950s and the 1960s, some government groups actually got together and passed a number of pieces of legislation. So the first one that was passed was what they call the Air Pollution Control Act of 1955. That's really the first one that kicks everything off. And the really important thing that it does is it actually allocates federal funding to do research on the causes and the effects of air pollution. Then 1963, you have one of the first iterations of the Clean Air Act. The Clean Air Act of 1963 expands that research and then also creates public health programs centered around that. So that's good. Then 4 years after that, they have in 1967 the Air Quality Act. Now this one's really important because it did something that up to that point had never been done, which is the Air Quality Act of 1967 established in law that states and local governments were the ones who should really be in charge of solving their own pollution problems. Full stop. Okay, we stop there. We say, great. Sounds really conservative, right? Solve problems on the local level. But the Air Quality Act of 67 went a step further because it said, okay, states and local governments, you guys have to solve this problem. But it also said that if they didn't do it adequately, then it gave the federal government the authority to step in and make them do things if the state failed to adequately act on its own. So, those three pieces of legislation were precursors, if you will, that in 1970, the landmark Clean Air Act of 1970 essentially was built on all three of those past precursors. And so the Clean Air Act in 1970 has this newly formed government agency, thank you, Richard Nixon, called the EPA, the Environmental Protection Agency. And the Clean Air Act gives the EPA legal authority to do what? Legal authority to regulate pollution from cars and other forms of transportation. And so the EPA says, thank you very much. That's going to make our job easier. And so the EPA starts partnering with states like California to try and fulfill its mandate, to try and regulate pollution from cars and buses and other forms of transportation. And the primary way that the EPA does this is by adopting increasingly stringent standards in a number of key areas. So, by any accounts, the the Clean Air Act has really been a rousing success. It's been one of the biggest successes, I think, of our lifetime. I mean, in the kind of polarized society that we live in, we have big government people and we have small government people, progressive and conservative. And people can complain all they want. They have the right to complain all they want about how government, how they think government needs to be smaller. They don't want the government telling them what to do. Government needs to stop interfering in their lives, yada, yada, yada. Okay, people have the right to do that. But at the same time, most of those same people like clean air. They like clean water. They like their environment to be, something that's not going to kill them. And any way you look at it, the Clean Air Act has served a really important, vital role in forcing people to make changes that have helped make our environment a lot cleaner than it used to be. So, how much cleaner, I guess, is the question that we want to ask. I mean, we can say, oh yeah, the Clean Air Act's been really big success, but let's put that into perspective by examining a few things. I mean, all of these rules, all of these regulations that the Clean Air Act has been responsible for, exactly how much effect have they had on what they were trying to do? Well, let's look at it this way. Let's go back in time to, let's say, 1980. This is 2023. You're talking about over 4 decades, 43 years ago. So 1980, if you look at the size of the economy that we have now versus the size of the economy back in 1980, essentially our gross domestic product is 3 times what it was in 1980. So our economy has tripled. Obviously, our population has grown, but our economy is 3 times what it used to be. So keep that in mind first. Then take that and say, if you look at the levels, the measured levels of these different pollutants, if you look at carbon monoxide today is 1/5, 20% of what it was back in 1980. Another way you could say that, it's gone down 80%. And remember, it's gone down 80%, but 3 times the economy size. That's huge. What about NOx? NOx emissions are about 80% of what they were. There's another one called SOx, which is really more applicable on the diesel side. Sulfur dioxide, things that contribute to acid rain that kill the, that come down and kill the forest. Sulfur dioxide emissions are 15% of what they were. In other words, they've gone down 85% since 1980. Remember those particulates that we talked about, those partially burned PM hydrocarbons? They didn't start measuring those rigorously until the year 2000. So if you just go back to the year 2000, we are down 40% from what we were back in 2000. And then the last one, ozone. Ozone across the nation is down by an average of 32%. So a third lower than what it was in 1980. Now, interestingly, go back to Los Angeles, the place that had the really high ozone levels. If you go back to Los Angeles, the ozone levels in LA today are 40% of what they were in the mid 70s. They're not down 40%, they are 40%, which means they're less than half of what they were in the mid 1970s. But get this, LA has more than twice the number of cars in it today than it did back in the mid 70s, and yet the ground level ozone levels that really kills children's respiratory systems, less than half of what it was. So those are all things that we can cite when we say we've done a reasonably good job of attacking this air quality. And one of the things that has contributed to this, that has been an instrumental tool for us as a society addressing this problem, is what we have done about what I would say is the elephant in the room that people for a long time really did not want to acknowledge, and that is addressing the role of cars and automobiles in this bad air quality problem. So, um, interestingly, when we're talking about cars, when we look back and we at when the research was first being done on this, when people were first looking at this problem, people were generally in denial that cars had any meaningful contribution to this problem. They wanted to blame something else. They looked for anything else to blame other than the fact that it was car emissions. That was really the primary driver. And so you had this biochemist at Caltech University in California named Arlie Hagen-Smit. And he was the first person, the first academic, if you will, to demonstrate that hydrocarbon emissions from car tailpipes, when you combine them with light and NOx emissions, they all combined together and turned into photochemical smog. He was the first person that showed this. So he does this research, he discovers this link, and what everyone realizes what the implications of this is. The implications is that cars really are the biggest culprit when it comes to LA's smog problem. So naturally, the oil industry and the automobile industry said, we're sorry, we didn't know we were causing such a problem, let us fix that. Well, no, of course they didn't, right? No, they pushed back, and they pushed back hard. And one of the interesting things they did was they actually sent someone from this institute called the Stanford Research Institute. You'll have to forgive me, I think it may be affiliated with Stanford University, but I'm not 100% sure. But one of the things that was known, or is known now, about the Stanford Research Institute is that it was primarily funded by the oil industry. So they sent one of their own funded academics to Caltech to discredit Hagen-Smith's work. Well, that was a mistake because, first of all, it made him mad, and it made him determined, or more determined than ever, to prove them wrong, to prove that his research was valid and that his conclusions were valid. And so that's what he did. He doubled down on his efforts, and he essentially won the battle. By the mid 1950s, there really wasn't any doubt left that cars really were the primary causative factor in LA's smog problem. So that's when it all started. So if we skip forward to today, we've had decades of advances in car design. We look at how today's cars are versus the cars back then. There have been some really big positive changes. So if we compare new cars and SUVs today to the new cars that were being sold in, let's say, 1970, new cars today, when you talk about the pollutants that contribute to air pollution, so hydrocarbons, carbon monoxide, nitrous oxides, and PM particle emissions, those things. New cars and SUVs today are 99% cleaner. They emit 1% of the air pollution that they did back in the day. That's pretty impressive. So today's cars are cleaner, they're a lot more efficient, they're a lot less polluting. So if we've essentially solved the car problem, I mean, there's always incremental ways you can improve upon that. But by and large, if we say, in that respect, we've solved the car problem, there's still another area that we can address that has the potential to further help substantively with this air pollution problem, and that's on the fuel side. So they had this research that showed that if you add oxygenates to gasoline, if you increase the oxygen in gasoline, you can positively reduce certain air pollutants that are produced when it is burned. You can reduce carbon monoxide by about 20%, and you can reduce what some academics call VOCs, or volatile organic compounds. Really, what they mean is unburned hydrocarbons and partially burned particulates. You can reduce those if you increase the oxygen in the fuel, you can reduce those by about 30%. Those are substantial changes. And so, since there's this evidence that this relationship exists, that this is true, now it was a matter of forcing the marketplace to do something. Because as we know, the private sector marketplace most of the time are not going to take these kinds of actions all by themselves. It takes the government with a big stick to force them to do that. And so that is what the government did. Sometimes it takes government intervention to force the private sector to do things for the common good. So the government says, we're going to make some rules that say the fuel composition needs to change because it's going to help in these areas. And so now we start talking about legislative efforts. So oxygenate compounds, what we started off talking about. Oxygenate compounds are not something that just came along in the last few years. They've been around and been put into gasoline for a pretty long time, since almost the turn of the 20th century. If you were to look through the 20th century, you would see, like, for example, the state of Nebraska in the 1930s was marketing this thing called gasohol, which is an ethanol blended gasoline. So this idea of putting oxygenates in fuel, whether to help with emissions or for some other reason, has been around much longer than a lot of us realize. And so when you talk about things at the federal level, making rules to try and make people do these things. So let's say the federal government wants to make a rule. They determine that we need to have more oxygenates put into gasolines because it's going to help with air quality. So one of the things that they're going to need to do, or I should say one of the things they're going to need to define better is what kinds of things, what defines an oxygenate that you can put into fuel that won't cause harm? And so when we introduce that concept, the reason we want to talk about that is that the federal government in the 1970s, when they were considering this, they realized that they needed to have a guideline, I don't want to say concept, but something, a way to determine whether you could put a proposed oxygenate in the fuel versus whether you shouldn't put it in there. And so they introduced in the 70s this concept called the substantially similar approval. Formally, if you want to put it that way, it was the substantially similar waiver concept was introduced in the 1977 Clean Air Act version. If you read through the 1977 Clean Air Act, in the amendments, it talked about defining requirements for what it called substantially similar gasoline. That means gasoline that has oxygenates in it, and those oxygenates themselves are substantially similar in makeup to the fuel itself. And so the 1977 Clean Air Act required that those kind of oxygenates be approved by the EPA and then be allowed to be put into gasoline. So what do they mean by substantially similar? Interestingly enough, it's the same concept that they use for fuel additives. What they mean is they say that in order for you to put something into on-road gasoline, and they also hold this true for diesel as well, but in order for you to put something in on-road gasoline, whether it's an oxygenate, or whether it's some kind of fuel additive, the litmus test, if you will, is that the elemental composition of that thing has to be substantially similar to the elemental composition of the gasoline itself. Now, what do we mean by that? What we mean is that elementally, it can only contain the same kinds of elements as what's already in the gasoline. So if you think about it, gasoline, what does it have in it? What are gasoline molecules made up of? Well, they're made up of a lot of carbon, first of all. So that's one. You've got oxygen in there, of course, number two. You've got hydrogens. You've got nitrogen. And then you've got smaller amounts of things, like you've probably got some phosphorus. You may have a little bit of sulfur, not much. But basically, you've only got a very limited number of elements that are already in gasoline. What you don't have is you don't have weird things like you don't have iron, you don't have aluminum, magnesium. I don't know, you don't have plutonium, that kind of stuff. And so, what the EPA in the 1977 Clean Air Act was saying is that they were saying, look, we want you to start putting these oxygenates in there, and we're going to approve a certain number of oxygen. We're going to tell you the oxygenates that you can put in there, and the criteria that we're going to use to prove them is that they can be shown to be, from an elemental standpoint, substantially similar to gasoline. And so that's what they did. 1978, they kicked things off by officially granting ethanol, ethyl alcohol, this substantially similar approval, what they called a waiver, to allow it to be put into gasoline. And if you know anything about the chemical structure of ethanol, ethanol is a really simple molecule. It's two carbon molecule, carbon, carbon, and then you've got hydrogens, and you've got one oxygen and a hydrogen. Only contains, three elements: carbon, hydrogen, oxygen. It is, by nature, substantially similar to fuel, so you can put it in. So 1978, the federal government grants ethanol, substantially similar approval waiver, to be added to gasoline. And so that really kind of kicked things off, because after 1979, they also capped it. I should have mentioned this. They not only approved ethanol to go in there, but they set a maximum cap. And that's important because you don't want to put too much of these kinds of things in gasoline, or it will essentially compromise the combustion characteristics unduly. So 1979, ethanol starts legally being allowed to be put into gasoline at a 10% maximum level. 1981, they say you can put some methanol in there, not at 10%, at a lower level. Then, also in 1981, they say that you can put this thing called MTBE into gasoline at 11%. And so all through the 1980s, the two biggest oxygenates that were put into gasoline were MTBE and ethanol. Methanol was a way distant third, because methanol has some problems that are associated with it. And then 1988, they bump up the MTBE. They say 11% was good, let's make it 15%. And so from 1988 on, you could put up to 15% MTBE in your gasoline. And whether it's ethanol, whether it's MTBE, whether it's methanol, all of these were allowed because they all were determined to meet this substantially similar legal criteria. So that's what the federal government was doing on this. But the federal government have never been the only people willing and able to take action on things like this. There were states that also were starting to take the lead themselves. And we start to see more of that happening in the late 1980s. And there's two big examples. First of all, 1988, Colorado. Colorado really becomes the first state, or they implement really the first regulatory program that requires the use of oxygenates in winter gasoline in Colorado for the purpose of reducing carbon monoxide emissions. Okay, so Colorado kicks that off in 1988. 2 years later, the federal government's looking at Colorado, right? And they're saying, Colorado, that was a very good idea. And so the federal government essentially copies what Colorado's doing. And they issue their own amendment to the Federal Clean Air Act, this time of 1990, Now the federal government says, we're going to make you do kind of what Colorado's doing, except what we're going to word it a little bit differently. This is what the federal government says. The federal government says that for winter gasoline, because remember, Colorado's rule was for winter gasoline. So the feds say for winter gasoline, you have to put something into the fuel that will increase the oxygen level up to about 2.7% by weight. But they say, but we're gonna, not every area has to do this. They say, we're gonna only require the areas of the country that consistently exceed or violate the federal standard for carbon monoxide in the air. So that's what the feds do in 1990, but then they also do something else in addition. They also say that we're not just going to look at carbon monoxide, we're also going to look at ozone. We say for those areas that have consistently high ozone pollution, we're going to require you to use reformulated gasoline, which is really just another way of saying oxygenated gasoline. Your reformulated gasoline that you're going to have to use if you're in one of those ozone high areas is going to be one that has an oxygen content of at least 2% by weight. So Colorado started this. Federal government piggybacked on what they were doing and issued new requirements for problem areas that consistently violate carbon monoxide and ozone emission standards. Okay, so meanwhile, California is looking at all this. They're over here standing in the corner. They're looking at all this. California's saying, that's a really good idea. I think we'll do something just ourselves. And so what California does is they say, okay, we're going to, Colorado and the feds, you talk about, winter gasoline. We're going to do that too. So California establishes, starting in the winter of 1992, they established their own requirement for wintertime oxygenated gasoline. What defines it for their purposes is an oxygen content of 1.8 to 2.2% by weight. So they start this in 1992. But then they say, well, we really need to do something for the non-winter gas as well. And so almost at the same time, they adopt additional regulations. And they adopt this term, cleaner burning gasoline. That's the term that California used. And they say, outside of the wintertime, you need to use cleaner burning gasoline. And cleaner burning gasoline, from their standpoint, is defined as gasoline that meets this high oxygen standard. So California basically becomes the first area to start requiring this oxygenated gasoline all year round. Now, so the last thing that we're going to say about that, that's what those states are doing. That's what the feds were doing through the 80s and into the 1990s. The one notable thing about what California did, apart from the fact that they were requiring something to be done all year round, the interesting thing is that they defined, cleaner burning gasoline, wintertime gasoline. It was only defined by oxygen content. What they didn't do, what California didn't do, and what nobody else did really, was they didn't specify what you had to put in order to meet that requirement. Now, they did that on purpose, or didn't do that on purpose, because they wanted to leave that choice up to the refiners. So what this means is we have a situation where by the early 1990s, both the federal government and the states have made these oxygenated gasoline rules. They're on that train. But they've really left it up to the refiners out in the private sector on what they want to choose to put into that gasoline, whether it's summertime or wintertime gasoline, to meet these requirements. So people have a choice of how they want to obey this. So if you were a state entity, right? If you were a state entity that was making a decision on what to put in your gasoline in order to make it comply with this, with these rules, The question that we're going to ask as we close out this episode 24 of the Fuel Pulse Show podcast, the question that we're going to consider and start to answer next time is, what factors would drive our choice on what we would choose, right? I mean, is it going to be cost? Is it going to be handling? Whatever. Because not all, even if all oxygenates can get you to this 2.2% oxygen content, that doesn't mean that they're all going to be equally right for your situation. And so the next time on the Fuel Pulse Show podcast, we're going to talk about the decision-making processes that these states and these entities went through and why they settled on this one big thing, MTBE, to be their oxygenate of choice. And then we're going to talk about how after it had become the dominant thing in the landscape for the U.S. fuels picture, suddenly they start seeing some problems, and they ain't small problems. They're pretty big problems. And what they did to solve those problems. So we're going to talk about all of those things on the next episode. That's going to wrap up the episode for today. Thank you very much for spending some time with me talking about this little slice of history. We'd appreciate it if you haven't done it already, if you would subscribe to the Fuel Pulse Show podcast on your podcast source of choice, whether it's iTunes or Stitcher or some other medium. Definitely tell your friends. And also, if you would go on to those and leave us a review, that's also something that really helps us a lot. So anyway, that's going to be it for today. Once again, I'm Eric Bjornstad. I'm the host of the Fuel Pulse Show podcast, and I will see you later on the next episode of the Fuel Pulse Show podcast.